All right, let's get started for real. Welcome everybody. Today we're going to talk a bit about assembly language and also the architecture of the processors that are going to execute our code. In the interest of understanding a little more detail how our code actually runs, so we can think about how we might make it faster on those machines. Oh, and a quick announcement. Please don't forget that your status reports are due today. I think that's the major deadline we have right now. Sorry, my controls aren't working. There we go. All right, so you've all been working with C code for at least a little while, hopefully, maybe before this class, but at the very least in this class. And you're probably getting a teeny bit familiar with the tools that we have to compile and run C code, a teeny bit familiar at a minimum. If you look at the make files that we use to compile our C code, we start off with some C source. That goes through some kind of compilation phase where you invoke, in our case, the Clang compiler. That produces some machine code. And then you can invoke that machine code which asks the hardware to actually execute it. And then that ultimately gives you your running program. So first thing now we're going to do is to start breaking into this compilation phase. And it turns out that there's actually 4 major stages to that compilation phase. And we'll talk more about this in the next lecture on Tuesday, but at a high level, the 4 major stages inside compilation are what we call pre-processing, compiling, which yes, is a little bit redundant because that's also what we call the entire pipeline. I'll say what that means in a second. Then we have assembling and finally linking. Sorry, I'm still losing control. So now to see what those 4 stages are all about, let's consider the case of a program, in this case made up of 2 different source files, which is we need more than one in order to make the linking phase interesting. So here we have a source file collision.c and another one main.c, and those run through our 4-stage pipeline to ultimately produce a binary that we can execute. So this first stage, pre-processing, takes the C source, including preprocessor macros, things like pound defines and pound includes, and kind of unrolls and inlines the results of all of those preprocessor macros to just produce unadulterated raw C source code. So everywhere you have a pound include, this is literally going to copy the text from that included file and stick it into the same stream of C source code. The output of that we call preprocessed source. We run that preprocessed source through the compile phase. That gives us some assembly code. Then the assembly code is creatively assembled to produce an object file. And ultimately, we can link together one or more object files, potentially also with other libraries on our system like libc or OpenGL or something else to produce our final binary, which we can execute. Somebody is not muted. If you guys could mute yourselves, that'd be great. Thanks. And then on the right-hand side here, I'm showing, normally when we invoke the C compiler, like when we invoke Clang, it basically runs this whole pipeline for us all at once. So we don't see these individual steps. But it turns out that there's flags we can pass to the compiler, which we're showing on the right, that basically tell it to stop at one or another of these steps and give us the intermediate output at that point. And a question came through asking whether pragmas like loop unrolling happen during pre-processing or later. And that's a great question. I think in general, so those are not the pragma, hash pragma keyword is something that's interpreted by the preprocessor, but that basically generates metadata that's then carried through to the C compiler. It's a way of injecting additional metadata about your code that can then be used by the C compiler downstream. So you don't literally do the unrolling in the preprocessor, although you could write macros that are equivalent to unrolling. That unrolling is being carried through the preprocessor as an annotation that then the C compiler can use internally when it's generating code during the compile phase. Good question. All right, so that's a bit about the pipeline. And what we're going to focus on in the first half of the lecture today is the assembly part of this pipeline. And there are several ways that we can work with assembly. One of them is just, like we saw on the last slide, we can start with some C source code and ask our C compiler to just emit assembly code for us. So in the case of Clang, we pass this -S flag, and that says instead of emitting executable machine code, please stop with just human readable assembly code and give us that. And what this assembly language is a human readable symbolic representation of the machine code that our processor is actually going to execute. So it corresponds very closely to, but isn't exactly the same as the binary machine code that our processor is going to execute. And then once we have some assembly code, we can, read and try to understand it. We could potentially even edit it. And then when we're done, we can again pass it to Clang to assemble into a final executable machine code. And the key thing with assembly in contrast to C is that it corresponds very closely to exactly what our processor is going to see and actually execute. So again, it isn't the exact same binary format, but it's basically a different syntax for the same exact instructions that the processor is going to see. And it turns out we can also go the other way. So, suppose we have a binary sitting around on our machine, maybe one that we don't even have source code for, and we want to take a look at what is inside that binary in terms of human readable assembly code. So there's different utilities on different platforms. On Linux, there's a utility called objdump for object dump that can help us with this process of disassembling machine code. So translating binaries back into human readable machine code. And if you invoke objdump on a binary with the appropriate flags, it's going to give you output like you see on this slide. What we have here is a combination of the machine code as hex values. That's kind of this brown column in the middle. I think the left are labels with the actual byte offsets of where those instructions are in the code. And on the right, you have more readable, human readable assembly code. In addition, you see a few interesting things in these semicolon comment lines. Objdump, in this case, because our binary was compiled with debug symbols, so compiled with the -G flag to our compiler, it's able to give us a little bit, it intersperses a little bit of the C source that these things actually correspond to, which can be really helpful in being able to more quickly read and understand what the different chunks of assembly mean in terms of C syntax or where they came from in the original program. Okay, so that's pretty cool. So we can go between C source code and assembly code and binaries, or even back from binaries to assembly code. But you might ask now, like, why should we be bothering looking at assembly in the first place? Assembly is really complicated. It's really ugly. You probably, it probably looks like gibberish to most of you at this point who haven't spent much time working with x86 assembly before. For many of you, I bet C already feels like a painfully low-level language. So, why do we want to go way lower level than that? I'm curious if anybody has some thoughts about why this might be a useful thing to do. Please go ahead and post in the Slack, and I'll give you a second. Why would we want to bother learning how to read and work with assembly code? I guess one idea that came up is security. I'm curious what you mean by that. Yeah, so reverse engineering for security, like trying to understand how a complicated, maybe obfuscated binary works. It could help us understand why a given high-level function that we have in C is fast or slow after we compile it. Yeah, we can see what the actual instructions are going to be at the level of more what the machine's going to execute, so we can figure out how to reduce work. Yeah, so in general, a lot of people are touching on the fact that it can help us understand what's coming out of our compiler so that we can make it even faster and and figure out how to optimize even further. And these are all great answers. So fundamentally, I think the most useful reason in the modern world to be able to read assembly is that the assembly reveals what the compiler did and didn't do to your code. And so when you're doing performance engineering, it can be really helpful not to just speculate about whether the compiler is going to succeed in doing a given optimization, but to be able to kind of inspect and validate the output and make sure that it didn't do something crazy. It turns out, there's some other reasons too. So bugs can arise at a really low level. All software is made up of bugs. You can sometimes run into complicated cases where a bug in your code might only actually appear when compiling at different optimization levels. It might be helpful to look at the different assembly to see why that might be happening. Sometimes, although you shouldn't assume this is the case, it's much less often the case than students are often prone to believe, at least with production compilers like we're working with, with Clang. Sometimes the compiler can even be the source of the bug. And so in my own work, we develop compilers. It's really useful to be able to read the output in order to be able to see whether there's a bug in the compiler somewhere. Some people touched on this. You can also write or modify assembly by hand in order to take extreme control over the code that you ultimately execute. And some people mentioned reverse engineering for the sake of security, but in our cases, it's also useful to reverse engineer existing code sometimes for performance. So sometimes you might want to take a program that you have sitting around, but you don't have source code for, and you might wonder how it's able to do something so fast. So for example, when we talked about optimizing matrix multiply, our speed of light example reference point was the Intel math kernel library. It's a closed source library that's incredibly heavily optimized. And it can be useful sometimes to be able to inspect what those experts did. They don't give you source code, but by disassembling their code, you can see kind of what the critical inner loops of their code are structured to do and how they're able to take such good advantage of the machine to better understand how you might get performance like that yourself. All right, so we're going to learn today a bit more about x86 assembly and how to read it, but there's a ton of details. So the modern Intel reference manual for x86-64 is about 5,000 pages long, and our goal here, it literally would obscure me in front of my camera if I put it on my desk, and our goal here is very much not for you to memorize that manual and be able to fluently read and write arbitrary x86 assembly purely from your head. That's not that useful for most engineers in the modern world. I work a lot at the assembly level and I don't have x86 memorized at all. But instead, what we really expect to do in this class, more than anything, is to be somewhat comfortable understanding how a compiler implements major C language constructs using the instructions of the underlying machines that we'll be running on. Again, that's the focus of the next lecture. And we expect you to be able to at least at a basic level, read and understand x86 assembly language with the aid of a reference. So like I said, I don't keep it all in my own head, but I know enough to be able to roughly parse it and to be able to look at references to understand the details where they're unclear. We expect you to be able to understand some of the high-level performance implications of common patterns in resulting assembly code, and potentially to be able to make simple modifications of the assembly emitted by a compiler, to be able to use intrinsic functions, which we'll talk more about later, and I mentioned in the matrix multiply case study, in order to be able to use specific assembly instructions not available otherwise in C, and potentially to know how to go about writing your own assembly code from scratch if you have some inner kernel that really demands it. All right. So with that, the outline of the rest of today, we're going to do a quick. Kind of the first half of the lecture is going to be continuing a quick primer on the x86-64 instruction set architecture, and then we'll talk a bit about floating point and vector hardware in the processors that we have, and do a little bit of an overview of key optimizations in modern processor architectures that let them run our code faster, so we can think better about how they're actually working under the covers. All right. So actually, I should stop quickly for any questions anybody has so far. Go ahead and shout out in the Slack if anything's come up. And then we'll start diving into details. All right. Seems pretty quiet so far. Cool. So let's dive into our quick primer on the x86-64 ISA. So much of this is going to be organized into tables that are really meant as convenient references for reading most of the assembly language you'll see in this class, so that you don't have to get out or Google that Intel assembly language reference manual. This will tell you kind of at a summary level, most of what you need to be able to parse a lot of common assembly code. Because of that, this part of the lecture is maybe a little bit dry because I'm mostly going to be kind of explaining to you how to understand these tables and what the key pieces are. But it's useful to know this, and you'll find yourself way better able to parse assembly code that may up till this point look like Greek to you. All right. So at a basic level, an instruction set architecture, I've been throwing around this word ISA or instruction set architecture, specifies the syntax and semantics of the code that our machine can actually execute. And remember that code actually has two embodiments. There's the binary format that the processor sees and the assembly format, which is how that's generally rendered to us as humans to work with. And the key pieces of the instruction set that we'll see are registers, instructions, different data types, and different ways of interacting with memory. So in this example snippet, you can see almost every line here is an instruction. Some of the arguments to those instructions are registers, so everything prefixed with a percent is a register, like this RBX that we have highlighted. There's also labels in the code, which basically let you reference the addresses of different pieces of code for the sake of doing branching, jumping around the code. And then you see two other ways data can enter as arguments to operations. We have both references to memory. So in this case, we have an indirect memory address. So we're loading a value. We'll talk about this more later from the address stored in a register. And then we can also have immediate values, things prefixed with a $sign, are basically constants in our code, kind of like constants in C code. All right, so let's pick apart the x86-64 ISA, and let's start first with the registers. So the registers, if you remember from computer architecture class like 6004, are basically the interface to a processor's internal state. And they're where we store the results of operations and various other state and condition flags. And it turns out x86-64 defines a lot of registers. This is going to be a recurring theme when we talk about x86-64 in contrast to like RISC-V, which I think you probably worked with in 6004. x86-64 is big. There's just lots and lots of registers, lots of instructions. It's a very complicated instruction set. But there's some basic structure we can learn to be able to kind of read it much more quickly. The kind of essential parts that matter are fewer than that. So this table summarizes most of the major registers. I don't think it's even quite all of them on the most modern processors. You can look at this on your own time, but again, for practical purposes, for the code that you'll work with in this class, you're going to encounter just a key subset of these most frequently, and we've highlighted them here. So you'll see the general purpose registers, of which there are 16, and they have lots of different names, which we'll explain in a second. You'll interact with the flags register called rflags. We'll talk more about what that does and what it means later. You might occasionally come across the instruction pointer register, RIP, which stores the actual current address of the instruction we're executing. And then you'll also see these XMM and YMM registers for floating point and vector operations, which we'll also talk more about later today. Question comes up in the Slack asking whether C inline assembly lets us access the actual CPU registers. And the answer is yes. So one of the key reasons you'd resort to inline assembly is if you want to control exactly which registers different data values go into. All right, so now a quick important note about x86-64 registers that you will see a ton is that lots of them are aliased. And this is especially true of the general purpose registers. By aliased, what I mean is that there's multiple names for different parts of the same thing. So it turns out for historical reasons, each of the general purpose registers is accessible as a 64-bit, 32-bit, 16-bit, or 8-bit register. And there's a different name for each of these. So on the slide, I've diagrammed the layout of one of the general purpose registers, RAX. And digging into that, you can see that so RAX refers to the entire 8-byte or 64-bit extent of the register. EAX is the name for just the lower 4 bytes, the lower 32 bits. AX is the name for the lower 16 bits, 2 bytes. And then we have these two names for the 2 bytes within AX, AL and AH, so A lower and A higher. I'm curious actually if anybody has any quick thoughts on why it is that we kind of have this recursion down to at least to 16 bits. And it kind of looks like the base name is AX, and then we added an E in front of it, and then we added an R in front of it. Does anybody have any thoughts on why that might be true in x86? Yeah, so the answer somebody brings up is you might need to run 32-bit or 16-bit code on a 64-bit system, which gets at the idea I was thinking of, which is the history of x86 is that it started in the 1970s as a 16-bit instruction set. It evolved in the late 80s to a 32-bit instruction set, and then in the 2000s to a 64-bit instruction set. And so effectively what we see is the AX register was the original thing, EAX is the extended version of that for the 32-bit extensions, and RAX is what we have in the modern x86 64-bit version. But they kept these around both for backwards compatibility and because it's sometimes useful to write code that can access just subregions of our data. Okay, so this is the full set of general purpose register alias names. You don't need to parse it all right now, but this table basically denotes the 4 main representations for each general purpose register ordered from left to right based on the location of the highest order bit and kind of the size. So we have the full 64-bit version and the sub 32-bit version and the 16-bit version and the 8-bit version. And those 8-bit ones, only the first 4 registers for historical reasons let you get either the first or the second byte. The rest you can only get the first byte. Okay. So that was a bit about registers. Now the next key piece of the instruction set architecture are the instructions. And these are the actual operations that we can perform. In an assembly code, they generally look something like this. So we have an opcode followed by a list of 0 or more operands. So the opcode is a short mnemonic identifying the type of instruction that we have, and often having some suffix or component that tell us a bit about the data type variants that it's working with. And then the operand list is usually 0, 1, or 2, or in the case of some advanced instructions we'll talk about later, occasionally 3 operands separated by commas. And for most of these operations, all the operands are sources, and then one of the operands might also be a destination. So in this example on the bottom, add L is the opcode mnemonic. Seems like we're doing something with adding numbers together. We'll talk about what the L means a little bit later. And then to the right of that, we have an operand list with 2 operands, %EDI, referring to the EDI register, and %ECX, the ECX register. And ECX here is both a source and a destination operand. So we're adding EDI to ECX and storing the results in ECX. Okay. Now, before we go further, one quick note about syntax for assembly languages that you'll see. Turns out that there's actually 2 standard syntaxes for x86 assembly that come up a lot, what's called AT&T syntax and Intel syntax. AT&T syntax, which you can see on the left here, is what we're going to use mostly in this class, what you're going to see coming out of all your tools like Clang and ObjDump and perfrecord and perfreport. But importantly, the Intel syntax is what you'll see used in the Intel documentation. And the key thing to note, more than anything else, there are fairly trivial translations between them, but there's one really big difference that can be easy to screw up. And that's what does the operand order mean? So it turns out in AT&T syntax, when we say op AB, what we mean is that B gets the result of B op A. And when we have Intel syntax, we mean the opposite. We mean A gets the result of A op B. So basically, in Intel syntax, the output operand is first, and in AT&T syntax, it's last. So just be a little bit careful about that because it can trip you up. But fortunately, there's a really easy way to know whether you're looking at AT&T or Intel syntax. Like I said, generally, when you're seeing things coming out of any of our tools or on our slides, it'll always be AT&T syntax, but it should be really obvious because the AT&T syntax has all these sigils in front of all the various names like $signs and percents and so on, and the Intel syntax doesn't have any of that. So if you see a bunch of extra funny characters, you're looking at AT&T syntax. All right, so any questions on what we've seen so far? I want to pause for a minute. Like I said, this first part's going to be kind of a wall of information, hopefully just trying to give you a bit of a structured understanding of how you can then be able to look up these references and get more familiar yourself when it comes time to read things. So we started talking about instructions, and the key piece of instructions that tell us what they do are what we call opcodes. And there's broadly 3 main types of opcodes, so 3 main types of instructions in x86-64. What we call data movement instructions. So these are things like move, which moves values between registers or between registers and memory, conditional move, which moves values between registers or registers and memory predicated on some condition code, sign and zero extension, and as well as some stack pointer manipulations. We also have arithmetic and logic instructions. So these include all the kind of integer arithmetic that you usually think of: add, subtract, signed and unsigned, multiply and divide, bit shifts and XOR and other things like that. Binary logic like XOR, which I guess I already referenced, and some additional Boolean logic operations, which are very similar to the binary logic operations, but don't have side effects. And then finally, we have control transfer instructions. And these are branch or jump instructions that take us, that move around where we're executing the code. So they take us to different parts of the code. So there's an unconditional jump that just always jumps to a different piece of the code. There are conditional jumps that follow a branch predicated on some condition being true. And then there's also some additional instructions related to making subroutine calls. Great question. So if you come from having studied RISC instruction sets, like the RISC-V you probably worked with in 6004, I believe it's all RISC-V these days, you've probably seen load store operations a lot. So generally, your arithmetic and logical operations can only take register operands, and then you have separate memory operations to move things between memory and registers. And it turns out, as we'll see a little bit more later, in x86, things are a little bit different. So we do have these data movement instructions. So like the move instruction is one way that you can do loads and stores. You can just say, move this value from this address to this register or vice versa, although they can also move things in between registers. But it turns out that those memory operands that you can pass to the data movement instructions, you can also often use one of them with arithmetic and logical instructions. And we'll see some examples of that later, I think. So the operands of add, subtract, multiply, divide, et cetera, can either be registers or constants or memory. And we'll unpack that a little bit later. All right. So now these are the general categories of operations that you see a lot, but in assembly code, one thing that you'll notice is that these base operation mnemonics are usually followed by some suffix. It's usually a letter or two. So that letter generally denotes, for data movement or arithmetic operations, it denotes the data type of what we're working with, and in particular the width or the size of data that we're working with, 8, 16, or 32 or 64 bits. And in the case of branch instructions or other conditional instructions like conditional move, it denotes a condition code, which we'll talk about in a minute. So in this example here, move Q, the Q means that we're moving a 64-bit integer. Okay, Q seems like a kind of arbitrary letter. Why is it Q? Well, again, we have a big table. So here's a list of all the x86 64 data types and how they correspond to data types that you've probably seen in C code. The leftmost column is the most common type declarations you'll see in C. Next, we have the literal format for expressing those constants, expressing those as constants in C. We have the size in bytes of those data types on x86 64. And then critically, we have the suffix mnemonic that you'll see in the instructions. And then the rightmost column is an interpretation of what that a kind of mnemonic interpretation of what that suffix stands for. So the single character stored in 1 byte is usually represented by the assembly suffix B. It's just short for byte. A 2-byte value in C, it's often called a short or an int 16 or uint 16. Represented in x86 by the assembly suffix W for word. Maybe a little bit weird. We're probably most used to hearing word refer to 32-bit things or maybe sometimes 64-bit things because we have a natively 64-bit machine. Does anybody have any thoughts on why words here are 16 bits? Yep, exactly right. It was developed in the 1970s. Back then, Charles made reference to this previously. word sizes on machines were a lot more diverse, and x86 started out as a 16-bit instruction set effectively. And so the word size was 16 bits. And then knowing that, it can start to make more sense of the other suffixes. You'll see the suffix L or D, most commonly D, I think, for 4-byte values. D stands for double word, because it's 2 times 16 bits. 64-bit values are referenced with the mnemonic Q for quad word. And remember, our pointers here are also 64 bits, so they're also quad words. Again, it's 4 times 16 bits. And then the floating point values you'll usually see S and D for single and double precision, or in weird archaic x87 code, which we mostly won't see or talk about, you might see T for extended precision. All right. So putting that knowledge to the test, let's look at a couple of examples. So it turns out that the 0 and sign extending move instructions in x86 actually take 2 different suffixes, one for the source and one for the destination. So now here we can see 2 examples, one of which move Z is going to be 0 extending, and move S is going to be sign extending. So it's going to be preserving the sign bit in the high bit position. Now let's just think about this first one for a second. What does anyone think that move ZBL means? What do the B and L mean? What types are we working with here? Any guesses? Phil is typing. Unsigned and signed. Good guess. But how we handle sign is actually encoded in the Z and the S. What do the B and the L mean? Byte and long. Exactly. So in this case, we're moving an 8-bit integer, a byte, to a 32-bit integer, a long integer. And on the right, we see L and Q. We're moving a 32-bit integer into a quad word or 64-bit integer register. Okay. So there's also really important suffixes on all the conditional instructions. So conditional jumps and conditional moves, you'll see using a 1 or 2 character suffix that's even more semantically important than the data size to indicate the condition code. So here we can see the instruction JNE. So the suffix NE, short for not equal, says that this jump should be taken only if the arguments of the previous comparison are not equal to each other. This previous instruction is compare of quad words of 2 values. It seems a little bit weird at some level. The jump is based on the condition of some immediately preceding instruction. It's not totally clear how these pieces are tied together. And to understand this in a little bit more detail, it turns out we need to look into one of those registers I mentioned, but we didn't explain, which is the rflags register. So it turns out on x86, all the arithmetic and logic operations that you perform, in addition to the output register that they potentially modify, they also update status flags in this rflags register. So, and what those status flags correspond to, you can see in this table on the left. So we have, some things for whether the results are 0, or whether they have a positive sign value, et cetera. And we'll talk about them more in a second. And so looking at a piece of example code, kind of like the previous slide, again, we see an arithmetic instruction followed by a conditional branch instruction. Here, the arithmetic instruction is saying we're going to decrement RBX, and as a side effect, that's going to set the 0 flag, the ZF flag, if the result is 0. So the 0 flag is going to be true if the result of that operation is 0, and otherwise it's going to be false. And then the meaning of this conditional branch instruction is that we're going to jump to this label LBB7_1 if and only if the 0 flag is not set. All right. So once again, we're in a situation where we have a big table with lots of stuff in it, but there's really a smaller subset of that matters the most for understanding most code and most of the code you'll work with in this class. So first we have the carry flag, which tells us whether the last ALU operation generated a carry or borrow out on the most significant bit. Maybe most significant of all is the 0 flag, which we'll see a lot, that tells us whether the result of the last ALU operation was or wasn't 0. We have a sign flag, that tells us whether the last ALU operation produced a value whose sign bit was set. And we have an overflow flag that tells us whether the last ALU operation resulted in some kind of arithmetic overflow. All right. So then the condition codes for our conditional jumps and conditional moves are the 8 that we have in this table. So you can see, there's a bunch of different codes with different kind of mnemonic meanings, whether it's equal, greater than or equal, not equal, whether there's overflow, et cetera. And then those are defined semantically in terms of some predicates on the state of different status bits in the R flags register that they check. All right. So a question to think about now, if we look at this, we can see that the E for equal and NE for not equal, putting it down here, E and NE, check the 0 flags register. So NE is if the 0 flag checks if the 0 flags register is 0, and E checks whether it's 1. So why do you think that might be? Anybody have guesses? Joshua Pan asks subtraction. I like where you're going, but could you expand? Binary comparison produces 0 or 1. Why does binary comparison produce 0 or 1? I think if you put those two together, we may be onto something. Someone's asking if bools are 0 and 1 for true and false. That's related, but not quite it. So it turns out that, and you might have covered this in 6004, but on x86 and lots of other architectures too, actually, hardware generally compares integer operands using integer subtraction. When we want to compare whether two things are equal, the general way we do that is by subtracting one from the other and checking whether the 0 flag, checking whether the result was 0, which we can see by checking whether the 0 flag is 1 or 0. So we can see things are equal if the 0 flag is 1. That meant that the difference between them was 0, or they're not equal otherwise. All right. So now I want to talk a bit about the different operands you can pass to these instructions. We talked about the different opcodes, the different operations we can perform, but we haven't talked that much about what different kinds of arguments they can take. So it turns out in x86-64, the operands of an instruction can take lots of different forms. So like a move instruction or an add instruction, in RISC-V, you might have seen like all your add instructions generally, I think, take register values and they produce register values. But in x86, it turns out that they can take lots of different things. So, and we talk about these different types of arguments often as addressing modes. So there's 3 different what are called direct addressing modes in x86. You can have immediates. I guess you would have also seen these in RISC-V, which are basically constants embedded in the code. So here, move Q of $172 into RDI says move the constant value 172 into register RDI. You can also, unsurprisingly, have register direct addressing mode. So we can move the value of the RCX register into the RDI register. And then we have direct memory addressing. So we can just have a constant address that we load from in memory. So we're moving the 64-bit value at the address hex 172 into the register RDI in the bottom line. But x86-64 also supports a number of different indirect addressing modes. So these are ways of specifying a memory address not just as a constant value. So the only memory address we had previously was that constant hex 172. We can also specify memory addresses as the result of some architectural state or some simple computation. So in the register indirect mode, we load from the address that's stored in a register. So in the first case here, we're taking the value in the register RAX, interpreting that as a memory address, and moving the value stored in that memory address into the register RDI. There's also a slightly more complicated form of this called register indexed, where we take the address stored in a register and add some constant offset to it. So here we're adding the offset 172 to the value in register RAX, loading from that value in memory and storing it into RDI. And then a special case variant of this is what's called instruction pointer relative addressing, which I think you're only allowed to do in some conditions. And that's in code, in assembly code looks basically the same, but we're using the special register RIP. So we're indexing data from memory relative to the current instruction pointer address. All right. And then we have one more general kind of mammoth monster addressing mode, the most general form of all these indirect addressing modes, which is what's called base indexed scale displacement. Kind of a monstrosity, but it looks like this. So we have move instruction here that's loading a value from some complicated expression pointing to memory somewhere, storing it in RAX. And the way we read that is like this. So the base address is stored in the first register argument, which is general purpose register. We also have an index stored in a different general purpose register, a scale, which is a constant, and a displacement, which is a constant. And the way we interpret this is that the address this is referring to in memory is equal to the base plus the index times the scale plus the displacement. And there's some constraints. The scale can only be 1, 2, 4, or 8. The displacement can actually be potentially quite a large constant. And then there's some rules for if you leave off different terms, what their defaults are. Now, you might ask why you want to do this. This looks kind of crazily complicated. And actually, I'm curious if anybody has any thoughts. What are some reasons why it might be useful to have an addressing mode that's this complicated? Johnny and Phil are typing. So a couple people mentioned the idea that maybe this is for indexing into arrays. Another idea is maybe for organization of stack frames. Yeah, it turns out that this is actually mostly about indexing into or streaming through elements of arrays. Although I suppose it's possible that you could also use this cleverly for reading values off the stack frame. But the reason we have like scaling on the index, for example, is that if you think about what you need to do to index into a multi-dimensional array, you often wind up kind of multiplying the extents of different dimensions by different indices and adding them all together. And you can either do that, you wind up with an expression that looks something like this, and you could either do that using just a whole bunch of regular arithmetic instructions. You need, in this case, at least 3 different arithmetic instructions to do these 2 adds and a multiply. But in this case, we're able to pack all of that into the address pipeline of our CPU. So we do one instruction that just sort of implies that a whole bunch of math is going to be happening along the side, not necessarily tying up, or requiring executing a whole bunch of additional intermediate instructions. So we've kind of compressed a whole sequence of operations into one compound instruction. All right. And the last thing I want to say about the arguments are the arguments that, there's one other type of instruction takes a different kind of arguments, and these are the jump instructions. So the jump or branch instructions, jump or the different conditional versions, take a label, which is a pointer to somewhere in the code as their operand. So labels can be symbols, they can be constants for exact addresses, or they can be different kinds of relative addresses. Most often you'll see jump to labels. And then occasionally you'll see what are called indirect jumps, which take as their operand an indirect address stored in a register. So you see that down here on the bottom with jump to the address stored in EAX. All right, so any questions so far? We're almost through the x86 assembly bit. Again, like I said, you don't need to memorize all this. We're trying to kind of summarize the key pieces you can use to kind of structure and understand what's going on without memorizing every single instruction and every format of it. And you'll probably find for the first while when trying to read assembly code, you just have a copy of the PDF of these slides open, and you can just flip through the different tables to look up what you need. All right, so I want to wrap up the assembly bit by talking about a couple different idioms that you will see in generated code that that can be a little bit confusing at first, It's a little bit surprising. You may wonder what the hell the compiler's doing. The first of those is a clever use of XOR. So the XOR opcode is in XOR AB. Unsurprisingly, computes the bitwise XOR of operands A and B. One of the patterns you might see is like we see on the bottom here. We XOR RAX with itself. That's a little bit weird. It's probably not something you'd manually be writing in your code all the time. I'm curious if anybody has any thoughts on what that means, why we might be doing that. Yeah, exactly. A bunch of people got it. Great job, everybody. This effectively sets RAX to 0. The XOR of any bit string with itself is going to be all zeros. And so this is a, sorry, I have a flash flood warning in my area. This is going to set be a quick idiom for setting values to 0. There's no other x86 instruction for zeroing things. This lets us just trivially do that. Cool. All right, a second idiom that you're often going to see is test of a register with itself, immediately followed by a conditional operation. Now, what the test instruction does is test AB is basically the same as AND of AB. It computes the bitwise AND of A and B, but instead of storing the result in B, it just throws the result away. So the only side effect, it only has meaning via the side effect of modifying the R flags register. Given that, what do you think this idiom means in these two assembly snippets where we're doing test of some register with itself and then doing a conditional operation based on that? Does anybody have thoughts on what that means? I guess almost coming through. If a bit is set in RCX, or maybe said a little more simply, what's a simple description of what we're doing here? Yeah, exactly. We're checking whether it's not 0. This is we're ANDing it with itself. If the value in that register is 0, the result's going to be 0. If it's not going to be 0. And then both of these are using the equality, the equal or not equal checks, which check the 0 flag. So we're effectively checking whether the value in those registers is 0. All right. Now, a third thing you might see, the last of these I want to talk about quickly, are no-op instructions. And it turns out that x86-64 includes several different no-op instructions, including just NOP, NOP followed by an argument of some kind, and this weird instruction beta 16, which is just kind of equivalent to NOP, but encoded different in the binary, I think. And you might sometimes see these when you look at generated code in particular. So a question then is, if you see this piece of assembly code that actually was emitted by Clang in a piece of somewhat normal code, we have data 16, data 16, data 16, NOP with a word and some complicated address expression as the argument to that NOP. What do you think that does? Anybody? I think we're getting ahead of ourselves, but great answer. So architecturally, like in terms of the semantics of the result of this code, it does absolutely nothing. But the question then is, why would the compiler generate assembly with this idiom? Why would we be inserting NOPs all over the place? And Johnny already got to the meat of what this is all about, which is that this is mainly an optimization to change the layout of our instructions. So we're adding padding, like adding null values into our instruction stream so that we can shift around the alignment of the subsequent instructions that are going to come after this. And the main reason we might want to do that is it might be most efficient on some processor if the beginning of functions or something like that is evenly aligned to cache line sizes or something. All right. So that's most of the core of the x86 instruction set. And now I want to take Charles blast right through. I think I need a 2-minute stretch break. I'm going to give the same thing to everybody else. So we'll take a quick breather. I'm going to grab a glass of water, and we'll come back to talk a little bit about the floating point and vector instruction sets and the hardware underlying them and begin to talk about architecture. All right, so see you in 1 second. All right, back again. Thanks for your patience. So I want to talk a little bit about the floating point and vector hardware in our processor, how that manifests in the instruction set, and what the hardware underlying it looks like. So it turns out that x86-64 supports, we know everything we've been talking about so far is working with integer values, and x86-64 supports scalar floating point arithmetic via a couple of different instruction sets. So we have the SSE and AVX instruction sets that support single and double precision scalar floating point arithmetic, i.e. the float and double types that you see in C. And then there's also a more archaic, less common, but still implemented instruction set called x87 that supports single, double, and extended precision scalar floating point using, it's less commonly used for reasons we'll talk about in a second. And importantly, as we'll see also in a minute, the SSE and AVX instruction sets also include vector instructions. But even just for scalar math, it turns out that compilers generally prefer using the SSE instructions instead of the x87 ones because the SSE instructions are just a lot simpler to compile and optimize for. And that's basically because the SSE instructions on floating point look basically like the regular, the rest of the regular x86-64 opcodes. And they use a standard set of registers, in this case, the XMM registers, to store floating point data, whereas the x87 instructions are kind of based on a weird auxiliary stack machine architecture that's Intel developed in the 80s and kind of threw away and abandoned, but just leaves around for compatibility purposes. Now, looking at a snippet of code doing scalar floating point with the SSE operations, again, we see suffixes. The main opcode mnemonics look similar to what we've seen before, but the suffixes tell us something about the data types. So here we see the data types SD. We'll explain what that is on the next slide, but basically that's telling us we're working with scalar double precision floating point values. So these are scalar double values in C. Again, we have a table telling us all the different mnemonic suffixes that we have in SSE. And SSE uses these 2-letter suffixes to tell us about the data type. And the basic mnemonic is that the first letter tells us whether we're working with scalar S or packed, in other words, vector data with P. And the second letter distinguishes between single precision and double precision with S and D. All right. So I've mentioned vector stuff several times and packed and so on. So what does that mean? So it turns out that modern processors often have, and all the processors we're working with, the processors in your cell phones today, in your laptop, et cetera, as well as the Haswell chips in the AWS machines on which we're doing our benchmarking in this class, they all have, in addition to scalar arithmetic units, they also have vector arithmetic units. And the vector arithmetic units process multiple pieces of data in what we call a single instruction multiple data, or SIMD fashion. And we mentioned this briefly in my quick case study on optimizing matrix multiply, but we'll talk a little bit more about what it means right here. So in general, vector instructions work on some kind of like k-wide vector unit, where we have k denoting our logical vector width. In this case, we have a vector width of 4. So k is 4 here. And our vector unit's made up of vector registers. So each of these vector registers, instead of holding a single value, holds a vector of k separate scalar, integer, or floating point values. So here we have 4 values stored in each register next to each other. And then the computation happens on k different, what we call vector lanes, which are basically k parallel sets of arithmetic units containing integer or floating point hardware. And the key thing about them is that the control logic that maps from what instructions we're running to what happens in these lanes uses the same control signals across all the lanes. So we're basically executing in lockstep, doing the same thing on every lane at once, but just on different elements of our vector. And what that means is that vector instructions mostly operate in a kind of simple element-wise fashion. So the ith element of one vector register only is going to interact with the ith element of other vector registers. If we have, for example, a vector add, it's going to take 4 items in this register and 4 items in another register and add them together element-wise. And all the lanes are going to perform exactly the same operation, like that add, on their respective elements of the vector. We're not running completely different instructions on the different vector lanes. Depending on the architecture, there's constraints on how vector instructions interact with memory. So memory operands to vector instructions might need to be aligned, meaning that their address has to be a multiple of the vector width, although that restriction's mostly been softened on the more modern x86 implementations like the Haswell that we work with here. Some architectures also support some cross-lane operations, such as inserting or extracting subsets of a vector, permuting or shuffling the elements of the vector in different orders, as well as scattering or gathering from memory. So taking dispersed elements in memory and having like an address in every vector lane and gathering from that vector of addresses to get a dense vector of values or vice versa. Okay. Now, today, x86-64, including the processors we're working with, actually have multiple different vector instruction sets. So the first one of these to come about, again, like everything with x86, we're basically going to see a historical accretion of different things. The first one that we generally work with is called SSE. It was the first one to come about like 21, 22 years ago now, I think, in its first incarnations. And SSE supports 128-bit vector operations on integer, single precision, and double precision floating point values. AVX, by contrast, supports 256-bit vector operations, so the vectors are up to twice as big, on just single and double precision floating point values, so no integers here. They fixed that in AVX2, and they added 256-bit integer operations to the AVX instruction set. And in the last few years, they've introduced AVX 512, which increases the register length to 512 bits and provides some richer additional vector operations, including things like pop count can now be done in a single instruction correctly. But AVX 512, it might be available on a few of your computers. It is on my iMac, but is not available on the Haswell processors or even most laptops from a year or more ago that you'll probably be interacting with. So Charles points out that unaligned vector operations, even if your architecture supports them, may still be slower than aligned operations. That's totally true in principle. In reality, I believe it is the penalty has been reduced to close to 0, although it's often worth checking when benchmarking a piece of code. Padding and stuff for alignment can still be useful. Okay, so what about the differences between AVX, AVX2, and SSE? The AVX and AVX2 instruction sets, which again were added in the last decade, extend the SSE instruction sets in a couple different ways. So SSE instructions, again, use these 128-bit XMM vector registers. And they're also constrained, like previous, like the rest of x86, to only operate on up to 2 operands at a time. So they always, overwrite one of their input arguments to produce the output. And the AVX instructions, by contrast, can use the bigger 256-bit vector registers, and they can also operate on up to 3 operands at a time. So they can have 2 source operands and 1 distinct destination operand, which means they can do some operations without clobbering their inputs, and they can also do fuse, multiply, add with 3 separate operands. And lots of the opcode mnemonics you see in SSE and AVX are actually really similar to just the base scalar things in x86-64, but with some minor differences. So in this case, for example, The V prefix distinguishes the AVX and AVX2 instructions from the others. And the P prefix on integer operations, and it becomes a suffix you can see here and here on the floating point operations. That P refers to vector instructions, meaning that, again, those were packed operations as opposed to scalar operations. The very last comment I want to say about the x86 instruction set is that there's also aliasing in these vector registers. So just like we saw with the general purpose registers, the XMM and YMM registers are aliased with each other. So again, YMM, those AVX registers are 256 bits, and the XMM registers aren't a separate thing. They actually refer to the lower half of each of the YMM registers. All right. Any questions on any of this before we move on to wrap up with a little quick whirlwind tour of how to make processors fast? That's all we're going to say about x86 assembly language for now. All right. So now I want to talk a little bit about how modern processors actually execute streams of instructions, and in particular, how they optimize to make that faster. So, previously in your undergrad architecture course, like 6004, I think, you've probably seen a simple 5-stage processor pipeline, something like this. You might not remember all the pieces and how they're all fit together, but you remember there was some sequence where you kind of fetched instructions at the beginning, figured out what to do, executed them, and then wrote back the results at the end. And that was spread over a series of cycles in a pipeline. For our purposes, we can kind of summarize this, ignoring all the complicated connections, and just think about it as 5 main steps. So each instruction is going to execute over 5 main stages. So first, we have instruction fetch, where we're going to read an instruction from memory. We have instruction decode, where we're going to look at that instruction and figure out what units it's going to use, we're going to use to execute it, and also what register operands it needs. So we can extract those register arguments from the register file. Then we're going to have an execute phase in the middle, where we actually perform the ALU operations. And we have a memory phase, where we read and write data to and from memory. And finally, we have a write back phase, where we store the results back into the registers for later use. Okay, so that was the cartoon, simplified, most basic pipeline processor that you start with in an intro architecture class. A real modern processor, like the Haswell we're working with, looks something like this. So this is a diagram from a website of actually a friend of mine called Real World Tech, which is a great place to go look if you want to learn all about the nitty-gritty details of each major generation of processor architecture from Intel and Apple and everybody else. This is the Haswell microarchitecture from about 5 years ago that we're working with. And you can see it's a lot bigger and more complicated. But if you squint and look at the color codes we've assigned, it's actually still got a strong correspondence to the major phases we had here. So you can see on the left, we have stuff related to fetching instructions and feeding them into the pipeline. Then in the orange and yellow, we have stuff related to decoding and issuing instructions. Then in the blue, we have things related to actually executing ALU operations. In the green, we have things related to doing memory operations. You can see there's way more stuff going on in parallel, and there's also way more actual discrete stages. So the depth of the pipeline in Haswell, depending on what operation you're doing, is between 14 and 19 stages. So it can take up to almost 20 cycles to fully retire an instruction. Now, I think it's useful to think about all the details, the difference between that simple 5-stage processor and the complicated modern processor, from the perspective of all the problems that architects have had to solve over the years to actually make real code go fast. And modern architecture is really all about pursuing a few simple goals in keeping code from slowing down, pretty much, being able to run our streams of instructions faster. And we're going to talk today, in the rest of these slides, it's possibly run out of time, but I'll put the rest online, about a few different major ideas. We already covered vector hardware that lets us run multiple ALU operations in parallel from a single instruction. And then the rest of today, we'll talk about the ideas of superscalar processing, branch prediction, and out-of-order execution. All right. So broadly, I mentioned, I think the right way to think about all this stuff is not a random grab bag of tricks, but specifically pursuit of the goal of executing our program's instructions faster in less time. And over the decades of Moore's law giving us many orders of magnitude, millions of times more hardware to work with in our processors, architects have generally thrown that at the problem of improving performance in two main ways. On the one hand, by exploiting parallelism, letting us execute multiple different things at once, so we can finish faster by doing more things in every cycle. And on the other hand, by exploiting locality to minimize data movement. So we talked about caching a bit previously, and we'll talk about it more later in the semester. Today is mostly about instruction level parallelism. So how we can execute more things in parallel every cycle at the level of individual instructions. And the first most basic way of leveraging parallelism in our architectures we've actually already seen. If you think about it, what that 5-stage pipeline is actually doing is, from the perspective of one instruction, we've made it take longer. We've broken that one instruction down into 5 sequential steps that we run one after another. But if you remember, the reason we did that was because we fundamentally need to run this whole chain of operations by breaking them into separate stages that run in separate cycles. We can increase the clock speed, increase the cycle time, or decrease the cycle time, increase the clock speed. So we increase the rate at which we run these steps. And then when we think about a whole sequence of instructions flowing through the machine one after another, and hopefully you've seen pipeline timing diagrams, something like this, also in 6004 or similar. If we look from the perspective of a single cycle, we've actually already got instruction level parallelism. So each pipeline stage in our 5-stage pipeline, in our 5-stage pipeline is executing a piece of a different instruction in a given cycle. So we're actually executing parts of 5 instructions every cycle. So we have sort of 5-way parallelism in a sense. But the key problem with this is that this pipeline diagram is really idealized. And it's not always possible to just shove one instruction after another into our pipeline every cycle. Excuse me. And if you remember back to your architecture class, there's various different kinds of issues that can prevent an instruction from executing during its designated cycle that cause this processor pipeline to stall. So if we think about that same sequence of the first 4 instructions, maybe we have to hold some of them up and they can't actually progress for several cycles at key points. And if you remember from architecture, the main reasons that happens are what we call hazards. So these are different ways that the order in which the instructions are executing through the machine and the way those instructions potentially interact with each other mean that we can't just run them all at once, one after another. Does anybody remember what any of the hazards are that tend to get in the way of pipeline execution? The data hazard? Yeah, great. Waiting for memory to be read. It's like at least one more answer coming in. Branch prediction, read after write, write after read. Yeah, so these are all related to the key issues. So at a high level, I think we can think about the types of hazards that you have as 3 main things. You have structural hazards, where 2 instructions need to use the same functional unit at the same time. They obviously can't do that. If you only have one ALU, you can't have 2 things using that ALU to do different things at the same time. There's also control hazards, where fetching and decoding the next instruction to execute gets delayed by a decision about the previous instruction. So for example, if we have a conditional jump, we don't know the next address we should necessarily fetch and execute until we know what the result of the condition is. And then finally, we have what are broadly called data hazards. So read after write and write after read are examples of data hazards. And that's where one instruction, the arguments to one instruction, in some way depend on the result of prior instructions in the pipeline. So now let's look at some of the ways architects can deal with these different hazards to keep our process from stalling and making it faster. And let's start with the structural hazards. So if we go back to our 5-stage pipeline, the first thing you might notice is that we just have a single ALU to perform all the arithmetic operations in our program. But if we think about, you know, on the processor architecture we have, we look at all the different ALU operations we can perform. Some of those, like, you know, simple integer add or XOR or whatever, may have very, very low latency. They may take 1 cycle. Some of them, like integer multiply, take a few cycles. Floating point add and multiply take a few more cycles. And then things like integer and floating point multiply and divide can take really long times, 10, 20 or more cycles, and they're actually variable latency. So the key question then is, you know, we obviously don't want to be just waiting for 20 cycles before we do anything else if we're going to occasionally issue a division operation. So how might we deal with these complex long-running operations without inducing lots and lots of structural hazard stalls? And the key idea here, the key first way we're going to deal with that is by just saying, let's, you know, use some of the extra transistors Moore's law is giving us to have more functional units. Let's just replicate some of those units that we might have had conflicts, structural hazards on, so that we can do more stuff in parallel. So maybe our more complex operations like floating point arithmetic happen through separate ALU pipelines on separate hardware. And we even see, if you remember SSE and AVX, separate register files for these things. And then if we look at these different functional units, you may notice like the integer ALU is within a single pipeline stage. Floating point add here is being spread across a couple, multiply spread across a couple more, and divide is a single thing, but with a cycle taking potentially unbound or unknown amount of time. And that's reflecting the fact that these functional units might be pipelined. They can be pipelined fully, meaning that you can, you know, it may take them a few cycles to complete, but you could feed a new operation into them every single cycle. So the throughput is 1 per cycle, even if the latency is more than that. And that's true of our floating point add and multiply here. But floating point divide, for example, may be partially pipelined or not pipelined at all. So we're only allowed to issue one of those every few cycles, or only once it's completely done executing. And if we look at our real Haswell processor, you see, you know, we dive into the execution part. We see that indeed it uses a big suite of different integer, vector, and floating point functional units. And those are distributed across 8 different ports coming out of our issue stage. So this is taking this idea kind of to the extreme. Now, so that's a way we can avoid, you know, so we see we have a reason why we want to have multiple parallel functional units in order to be able to avoid structural hazards, avoid unnecessary stalls when we need to do long-running operations one after another. But if we think about it for a bit, it seems like maybe there's an opportunity to do even better with this. So once we put these extra functional units into our processor, you know, what's one way we could get even more parallelism out of it? Since I'm running short on time, I'm going to jump straight into it. It turns out there's this idea that came about a bit over 30 years ago in desktop microprocessors called superscalar execution. And the idea here is, hey, we have a whole bunch of parallel ALUs. Why don't we make it so that our fetch and decode stages, instead of only being able to fetch and decode 1 instruction per cycle, can fetch and decode multiple instructions per cycle? Because then we can keep our parallel ALUs fed at a higher rate. You know, we have a bunch of them. Why don't we just look at the next 3 or 4 instructions and see if we can jam those down the pipe each cycle instead of just one at a time? It's also the case, so if we dig into the fetch and decode stages of Haswell, we see a lot of this kind of superscalar parallelism. So Haswell breaks up x86 64 instructions into multiple smaller operations that it calls micro-ops, which are more kind of akin to the internal or the standard operations you'd see in RISC instruction set, like you might have worked with in 6004. And the fetch and decode stages can emit 4 micro-ops per cycle to the rest of the pipeline. So we have 4-way superscalar issue. And it turns out that they also implement some clever optimizations at this stage of micro-op processing. So if you remember like that special case idiom of XOR RAX with RAX, that's a very common idiom to just zero out a register. And so the front end of the pipeline, instead of actually using real ALUs to do that, can just directly say, okay, I know that means that I should just stuff a 0 in this register. And that there's extra hardware there that just recognizes that during decode and immediately does it. All right. So that was how we dealt with structural hazards. So now I want to quickly see how we can optimize our processor to avoid control hazards. So this is getting a little bit out of sequence or out of order, to make a pun, with how processor designs have developed historically. But I think it's a slightly easier thing to understand. So let's look at it first. So we think about what happens when our processor encounters a conditional jump or a branch instruction. If you remember the rough flow of our pipeline, the outcome of the branch, it's going to be evaluated, or the condition code that determines which way the branch is going to go is only known after the execute stage of the instruction that generates the condition. But the instruction fetch stage needs to know the outcome of the branch a number of cycles earlier, potentially 10 or 20 cycles earlier in the case of our deep Haswell pipeline, in order to know what instruction it should fetch and decode next. So to handle this, we really have two main options. So we can either stall the processor, and that's the naive thing that we started with our simple 5-stage processor, but with a deep 15 or 20 stage pipeline like we have in our Haswell chip, those stalls can be really long. We can be wasting tons of opportunity to do useful work. And the main other thing we can do is just speculatively execute past it. So when we encounter a branch, for example, we can just assume that the branch doesn't get taken and keep reading the code and executing normally. So here we're speculating on a prediction that the branch is not going to be taken. That works great if it in fact isn't taken, because we didn't stall or pause at all. But obviously, if we later discover that the branch was taken, then we have to roll back all the stuff that we've done, undo that speculative computation, and start again from where we left off. And the problem then, so the problem with just naively always predicting not taken, for example, is that the cost of undoing all that stuff is at least as big as just having stalled in the first place. So on Haswell, concretely, the cost of a mispredicted branch is like 15 to 20 cycles. So to get around this, the key idea is to be a little bit smarter. We don't just always assume a branch is taken or always assume it's not taken. We use what are called branch predictors to increase the accuracy of this speculation. And the fetch stage of our processors dedicates extra hardware to predicting the outcome of different branches. And this has been done with increasing complexity as our hardware gets bigger over many decades, to the point where today modern branch predictors on realistic code are more than 95% accurate. They'll guess right more than 95% of the time. And on loopy code, they often guess right, like 99% of the time. So we don't have time. People have thrown tons of research and architecture engineering at progressively more complicated schemes for branch prediction. We don't have time to talk about all of the state-of-the-art methods and everything everybody's ever tried, but a really simple scheme that gives you an idea for how you might do this and is actually the basis for often kind of simple first-order predictors. You often have cascades of increasingly complicated predictors in real pipelines today. And the simplest ones of those work something like this. The idea here is that in hardware, we're going to maintain a table that maps from instruction addresses where the branches are to predictions of their outcomes. And a really simple way we can do that, we're going to update those predictions based on what we see. And a really simple way we can do that is by using a low precision saturating counter to encode which direction we think the branch is going to go. So in this case, we use a 2-bit saturating counter. The kind of 2 upper values mean that the 2 larger values mean that it's taken. We predict the branch is taken. The 2 smaller values mean we predict it's not taken. And then every time we actually go through that branch, we update the counter based on the actual outcome of the branch when we evaluate it. So if it's taken, we increase the counter. If it's not taken, we decrease it. And this is the key part that I mean by saturating counter is, we don't wrap around when we increment the maximum value. We just stay at the maximum value. All right. This idea is kind of fundamental to modern branch predictor designs, but it doesn't get you all the way to 95% prediction accuracy. More complex predictors today incorporate lots of different history information. They record the outcomes of multiple different branches. They reason about correlation between different branches, as well as the local history on individual branches. They often incorporate different information from different sources in different ways. So you might have a tree of different predictors that then get combined or get to vote on what they think is going to happen. And as you might guess, in the modern world, people even throw machine learning at this. So one of the state-of-the-art techniques that was actually invented more than 20 years ago is to use a multi-layer perceptron, a small neural net, to predict branch directions. And I think that's been incorporated in AMD architectures for something like 10 years now. Finally, I just want to say that it turns out that there's not that much publicly known about the branch predictor in the Haswell processors we work with. There's some academic work that's been done studying in detail what its behavior on lots of different micro benchmarks is, and correlating that with different known types of design. And so people have made a pretty educated guess that it's something closely related to this page branch predictor idea. It stands for tagged geometric history length. But basically it's a complicated thing that does a pretty good job predicting branches as long as they aren't completely random, and is kind of at the crux of a lot of what makes our processor able to run branchy code fast. So that's all we have time for today. There's one more little segment in here on how we can reorder instructions to deal with data hazards using what's called out-of-order execution. I'll just put those slides online. That's kind of the last little piece of how modern processor pipelines optimize our instruction execution. You can just flip through those on your own time afterwards. All right, so with that, thank you. And I'll hang around for a little bit if anybody wants to chat. But that's it for the official lecture. Thanks.